right, so. He's not here. Lawrence is here. Bonner is not here. Ray is not here. Dawson is not here. Ellis is not here. Paul is not here. Green is not here. Harrison is here in red. Vincent is not here. Last name James is here in red. Kesterson's here in red. King is not here. Lewis is not here. Linda Q is not here. Morrison's here. Grace is not here. Ward is not here. Wilcox is not here. Wilder is not here. Parks is not here. Take a look at who's online very quickly. Let's see. Wilder is online. Don't forget, if you're online, you have to send the words before 9 a.m. to be considered present. Let's see, who else? Kyle is online. Ward and Trace are online. Lewis, King, and Bonner are online. Lewis, King, and Bonner. All right. All right, really quickly, Key. Nope. We have Dawson, right? Dawson came in red. Parks, I think everybody else is accounted for. Close the store, we'll get started. So just a heads up, I will be traveling this weekend. Family reunion / wedding anniversary. Starting today. So some of my office hours might actually be online instead of in person. I don't know yet. I'm definitely going to my office. I just don't know how long I'll be there. But either way, if I'm not in my office, I should be online. But I guess this is relevant to you because if you need me and I'm really slow to get back to you, that's why. I'm traveling. It's about 7.5 hours one way. Plus, then once I get there, I'll be spending quality time with my family. So I will be hard to reach. Another reason that's important is because you should keep an eye on your emails, especially before you come to class on Monday, just in case, things happen. I could get in an accident, could get carjacked, who knows? I could get stuck somewhere other than here. And if that were to happen, then on Monday, class would be 100% virtual. Now that I planned for it, that probably won't happen, luckily. If I didn't plan for it and failed to tell you guys that and remind you that, then something would go wrong. And then you guys would show up and I wouldn't be here. But anyway, yeah, so make sure you check your emails before you come to class on Monday. As a matter of fact, I might even send an email out on Sunday to remind you to check your email on Monday and include the link that these people who are currently online are using. So does anybody have any questions? Oh, yeah. Good question. Yeah, it is Indigenous Peoples Day / Columbus Day, and the only holiday we recognize in the fall is Labor Day, which is, we've already had. So Veterans Day, again, that's a good time to remind you too. We don't recognize veterans either, or at least not Veterans Day, so I've given myself the day off. Remember, it's a good reminder on November 11th. Class will be 100% virtual because I will at least not be coming in. I was maybe in my pajamas, still recovering from the weekend. So, any other questions? That was a good question.
Have class on Thanksgiving?
What?
Thanksgiving?
Oh, good point. No, that week, we do have that whole week off. Yeah, so yes, no class on Thanksgiving. So yeah, that was a little bit out of context, I apologize. We have the entire week that's our fall break. Any other questions? All right, let's get started. Oh wait, another good reminder. I have to double check this. I'm pretty sure the exam 2 is due on Sunday. Make sure you get that done. And don't make the mistake that 2 people miraculously made the same course, not this course, but one of my 108 courses. I got an email 2 minutes apart from each other that said they started the exam, but then they were at work, so then they had to go give a tour. Can they retake the exam? I'm like, that's awfully fishy. Because they both had the same excuse and both sent it like 2 minutes. Anyway, that part doesn't bother you. The point is, don't start the exam unless you know you've got 50 minutes to take. And be ready to also, when things go wrong, be ready to document anything that happens. Like if someone comes in, if for some weird reason you think you can get it done at work, have your camera ready, and if someone comes in and says, hey, I know you're working there, but you need to unclog that toilet because we've got the president coming in. Get your camera out and record it. Like, okay, boss, say that again so I can send this to my professor. Or if your Wi-Fi goes out, or tornado comes and blows away your computer, be ready to document some proof. If you just say, hey, I started the exam and something went wrong, that's not necessarily going to work. So make sure you're ready to document stuff. Any questions?
It's long.
It's the same, 50 questions, 50 minutes to take 50 questions. So you got 1 minute per question. Yeah, 50 minutes, 50 questions. And remember, the quizzes are the study guides. You can take the quizzes as many times as you want, and it'll never dip below your highest score. You score the full 20 points, and then you keep taking it because you keep getting different sets of questions. That's why I set it above that way. Even if you fail the next question, the next quiz with 0%, your grade is still the full 20%. Your highest grade you get is what you stay with. So keep taking those quizzes over and over again. They'll be in different orders. You should get different sets of questions. It'll be very good to help you study for that exam. All right. Any other questions? Okay. So again, before we move forward, the exam is going to cover energy stuff, right? So how cells work with diffusion, osmosis, hypertonic versus isotonic. But then a lot of it's also going to be photosynthesis and respiration. Whew. All right, here we go. So we finished talking about meiosis, so now we're going to do like a little review to help not differentiate, but remember the differences and the similarities between mitosis and meiosis, because a lot of the next exam 3, can have a lot of this information on it. So the events that are unique to meiosis only occur during meiosis 1. Another way of saying that first bullet point is meiosis 2 is basically the same as mitosis as far as how things operate. So that's an important thing to know. Let's see, the first word for attendance will be review. So meiosis 2, again, is virtually identical to mitosis in that when we're talking about mitosis 2, we're talking about, meiosis 2, we're talking about separating sister chromatids, right? When we're talking about meiosis 1, which is not up on, what I'm about to say is not on the screen, so it's just a good reminder. In meiosis 1, we're separating homologous chromosomes. In meiosis 2, they've already been separated, so now we're separating the sister chromatids, right? Another difference, though, between mitosis and meiosis 2 is the fact of the end product, right? So yeah, in both, we're separating those sister chromatids. But in mitosis, whatever you start with, you end with, right? So if you start with a diploid cell, you end with a diploid cell. In meiosis, the end result for humans, we have haploid daughter cells. So any questions about that review, right? It's all information you've had before. The next slide is going to be a visualization of everything that's right here. This picture is not from your textbook. This is from the old textbook. So if you like this one more than what's on your textbook and you want to study it, then you need to download the PowerPoint. But you can see here, mitosis is on the left, meiosis is on the right. Here we have every single one of the chromosomes lines up single file in the middle of the cell for mitosis. And then those sister chromatids get separated, and now we have full-blown regular cells that have a full set of chromosomes, hence the 2N. They're both diploid, right? So we started with 1, we ended with 2. 2 identical cells is the beginning of what we started with. Meiosis is different. So again, the first stage of meiosis, instead of lining up single file, they're lined up double file. because what we have here, instead of sister chromosomes, is homologous chromosomes. And on top of that, not only those homologous chromosomes together, but they're also, because they're together, crossing over back in prophase 1 of meiosis. That never happens in mitosis, right? The crossing over only happens in meiosis. So anyway, after the first round, again, we are separating the homologous chromosomes as opposed to sister chromatids. Then we're left with just the sister chromatids, right? So then we separate those sister chromatids as we did in meiosis or mitosis. And of course, here's the end product. We end up with 4 haploid cells as opposed to 2 diploid cells. We end up with 4 genetically unique cells because they're different from each other. I know it might be a little bit hard to see, but you can see each one of these has a different color scheme because they are genetically unique. And they're also genetically different than their parent cell. Unlike here, once again, we end up with what we started with, a genetically identical cells. They're identical to each other and identical to the parent cell. Any questions about this slide?
Are they called homologous because they're a pair and not?
Yeah, because homo means the same, right? That prefix homo means same, basically. So that's why they're called homologous, because they're the same chromosome, just different versions.
And then they separate.
Yeah. More importantly, and I hope this doesn't confuse you, but what we're looking at here is a bunch of sister chromosomes, right? There's 2 sister chromosomes, there's 2 sister chromosomes, there's 2 sister chromosomes, so on and so forth. We still have sister chromosomes over here, right? But we're also dealing with homologous chromosomes, and we're just kind of ignoring the fact that there are sister chromosomes. See, there's 2 little sister chromosomes, 2 little sister chromosomes, but together, those are homologous chromosomes. Those are 2 little sister chromosomes, those are 2 little sister chromosomes, together, they're homologous chromosomes. So those homologous chromosomes, sister chromosomes and all, are together. And then they separate, the homologous chromosomes separate, so then we're just left with sister chromosomes, sister chromosomes, sister chromosomes, and sister chromosomes. Great question. But to simplify things again, when we're talking about meiosis 1, even though technically there are sister chromatids there, we're not worried about that yet. When you think of meiosis 1, you should think homologous chromosomes. Only because that's what we're dealing with, that's what we're paying attention to. But again, they are still sister chromatids because they did that duplication in S phase of interphase. They're there, we're just not worried about them in the first round of meiosis. Great question. Anything else? Okay. Here we go. This is going to be very important. The origins of genetic variation. We've already been hinting at this. This is going to be very important, not just for this slide, and not just for this chapter, but next chapter too, when we start getting into genetics. And then definitely when we start talking about natural selection and the other types of evolution. You cannot have evolution. You cannot have natural selection. You wouldn't have life as we know it on Earth without the origins of genetic variation. I'll come back to this later when we talk about evolution, but even just one example is even talk to people who went to that Great Ark Experience or whatever it's called. That's the Creationism Museum, Kentucky. And even, I haven't been there yet, I want to go. Even that basically explains evolution. They just don't call it evolution. Because they claim, like for example, there was a great flood. They had 2 bears on the ark. And then after the flood, those 2 bears left and then recreated the planet. And as those bears went to different parts of the planet, they changed according to their environment. And therefore, now we have different species of bears. And that's exactly what evolution is. So, right, even if you don't call it evolution, and even if you don't believe that's how life started, which is fine, you still need to understand how it works and understand that it does in fact happen. And even people who say they don't believe in evolution, as that museum demonstrates, they do, they just don't call it. They don't like calling it that. So, yes, we would not exist without this genetic variation, even if you believe that we were created like that, 2 humans at once. But that's a different story. We'll cross that bridge when we get there. So, the offspring of sexual reproduction are genetically different from the parents and one another. That's an important thing to know. So again, we're talking about genetic variation. That is very important when we're talking about sexual reproduction. And remember, not everything reproduces sexually. For those organisms that do reproduce sexually, like us, in mammals and things that aren't bacteria, for example, all the offsprings are genetically unique, right? Of course, there's some exceptions. I don't remember what chapter it was, but I was telling you guys about parthenogenesis, which is where a female can basically clone herself and have offspring that are genetically identical. But generally speaking, they're all genetically different. And that is important, right? And when we talk about evolution and natural selection, you realize why that's important. For now, just know that it's very important. But then that brings up the question, how does meiosis produce all this genetic variation? Because again, remember, only sexually reproducing organisms go through meiosis. Everything else just does mitosis to reproduce, and they make a perfect copy of themselves. So in a sense, sexual reproduction is kind of like a step above asexual reproduction, in a sense. And you'll see what I'll talk about later when we get to that. Sometimes there's advantages to sexual reproductions, and sometimes it's more advantageous to have a perfect copy of yourself. So let's talk about the two things that are giving us our genetic variation. And guess what? If you can read this, we've already talked about them. So now we're just reviewing them. Independent assortment and crossing over. So both things that we talked about in this chapter, now we're just going to focus it. We're bringing them back because they're that important. And we're going to talk about them in more detail. Independent assortment. Here, you're going to need to know what this is. And this really isn't that complicated until the next chapter. Because the next chapter, I'm going to introduce you to something called, actually, I won't tell you yet, because it'll confuse you. Let me just let this soak in finally before we give you the new stuff. But this isn't that hard until next chapter when I give you another term that sounds similar. Then it'll be a little bit harder to try to remember which is which. But for now, just enjoy this relatively simple explanation. In metaphase 1, the side-by-side orientation of each homologous pair of chromosomes is by chance. And I tried to draw a picture of that on the board on Wednesday where I was like, all right, let's draw a bunch of homologous chromosomes lined up together. Right? Actually, you know what? I won't even do it that way. Instead of looking at the chromosomes, let's just focus on the fact that some are for mom and some are for dad, right? So I was just making the point that like if you had a bunch of chromosomes lined up in metaphase 1, it's not like all your mom's chromosomes are going to be on one side and all your dad's chromosomes are going to be on the other, like I just drew there, right? The way they line up is completely random. So you might, in fact, have a cell that looks like this before it goes through meiosis, or you might have one that looks like mom, dad, mom, dad, mom, dad, mom, dad, mom, right? That's just one variation, right? So imagine all the different ways I could draw how those are lined up with only 4 chromosomes, right? 4 pairs of chromosomes, excuse me. Now imagine the fact that we have 23 pairs of chromosomes. And like I said on Wednesday, a really horrible trick to do to a student would be like, all right, I want you to draw all 23 mom, dad, right? Mom, dad, 23 times in a row, up and down. And then I want you to draw every single variation that you could have of mom on one side, dad on the other. You would never get that done in this semester. And here's why. Let's look at some math. Again, humans have 23 pairs of chromosomes. So that means if you were to look at each one of you, and again, they all line up randomly, mom, dad, whatever, they line up randomly. So the math tells us that with 23 pairs of chromosomes, and basically, I don't want to get into it, but it's the next point, right? So there's about 8 million possible combinations. Meaning, if you were to look at any one of your sperm or egg, look at any one of them or any 2 of them, like the chances of you getting, like, I'm going to put this a different way. Statistically, if you were to look at 8 million different of your chromosomes, or excuse me, your sperm cells or your egg cells, each one of them would be different. That's only for independent assortment, and that's only your your sperm cells or your egg cells. Consider then, too, that your person you're procreating with also has the same numbers. So then mathematically, we do 8 million squared, and that gives us 64 trillion possibilities of which sperm is going to meet with which egg and which chromosomes they're going to have it. Meaning, based on independent assortment alone, the chances of you being exactly you is 64 trillion. If you could somehow get your parents to have 64 trillion offspring, statistically, each one of them should be genetically different than you. Now, obviously, some of them will be really close, and that's only with independent assortment. Keep that in mind. And I know this is, I mean, as far as the exams are concerned and understanding things I'm about to teach you later in the semester, this is really not that important. But to me, it's just really mind-blowing. Because I've used this scenario before. It's a little, I don't want to say inappropriate, but imagine, so then when your parents had sex, or if you were IVF, you know, however that happened, if they didn't do it in the exact position they did it, and if your dad didn't ejaculate exactly when he did it, then you would not be you. Because again, there's a 1 in 64 trillion chance of that specific egg and that specific sperm coming together. So if your dad was in a bad mood because he got cut off on the way to work in some alternate universe and everything else in the world was the same, you probably wouldn't be you, because maybe he would have ejaculated a little bit later because he was distracted because some jerk cut him off on the way home. Isn't that crazy to think about? Like, you would not be you if any slight thing in history was ever slightly different. It's mind-blowing to me. And once again, this is only talking about independent assortment, as I'm going to talk about here in a few slides. Then remember crossing over. So not only do we have 64 trillion possibilities of mom chromosomes versus dad chromosomes, but then keep in mind that sometimes it's not even. Like this right here, this says right here that's a mom chromosome and a dad chromosome. But remember, with crossing over, some of that mom chromosome is going to have some dad on it, and some of that dad chromosome is going to have some mom on it. So that's number of 64 trillion then just gets astronomically large. So once again, for the exam, for everything else I'm going to teach you in this semester, this thing that I'm going on and on about is relatively unimportant, but to me it is just mind-blowing. Anyway, back to independent assortment. Here's a great example. This is kind of the kind of stuff I was trying to draw, but it looks much better. Once again, this picture's not in your textbook, it's from the old textbook, but here we're looking at an organism that only has 2 pairs of chromosomes, right? Chromosome number 1 and chromosome number 2. And so this makes things a lot easier. In this case, we've got all the mom chromosomes on one side and all the dad chromosomes on the other. It goes through a couple rounds of meiosis. So what you end up with is 2 gametes with mom chromosomes, 2 gametes with dad chromosomes. Here, because they happen to, by chance, line up the other way, and remember, this is only 2 chromosomes, if it was, or 2 pairs of chromosomes. Imagine if we were looking at 23 pairs of chromosomes. Here we've got mom on one side, dad on the same side, dad on one side, mom on the same side. They go through a couple rounds of meiosis. So now we have all 4 of these gametes have both the mom and the dad chromosome. And again, that is an oversimplification, obviously, because if we're looking at 64 trillion different combinations, well, 8 billion in this case, but yeah. So that's independent assortment. So again, let's get back in the gears of thinking about exams. So for the exam, what you need to know is independent assortment is basically this right here. This is showing you the result of independent assortment, which is going to be a little bit less important as far as the exam is concerned. Just remember, independent assortment is saying they don't just all line up, mom on one side, dad on the other. They do it independently. It's all completely random. Another option, won't get there. Let's just keep that simple. So again, that's just a simplified version with 2 chromosomes. With 2 chromosomes, those are the only 2 possibilities. With 3 chromosomes, there's going to be a lot more possibilities. With 4 chromosomes, there'd be even more possibilities. But again, that's an oversimplification. So are there any questions about what independent assortment is? Okay. And again, I think that's pretty simple because they sort independently. That's pretty simple. But like I said, later in the next chapter, God bless you, later I'm going to give you a different word, and that might make this a little bit harder to remember. So try to remember this now while you can. All right. So again, that's only independent assortment. 64 trillion different possibilities of your mom's egg meeting, or particular egg meeting with that particular sperm. And then we didn't even consider crossing over, which we've already talked about, so let's talk about it very quickly again. Crossing over is the exchange of corresponding segments between homologous chromosomes. You already knew that. It occurs in prophase 1. You already knew that. And what it results with is gametes that have chromosomes that are partially from the mom and the dad, right? Here's a picture of that. So there they are, they're together. It's prophase 1. So you can see they're literally touching because they're so close, and then they just kind of swap parts. So now here you have a mom chromosome with 2 dad chunks on it, and then a dad chromosome with the corresponding mom chunks on it. And remember what I told you too, not that this is important for the exam or for anything I'm about to teach you, just to help you realize how insanely small the chances of you being you are. Remember, sometimes crossing over doesn't happen. Sometimes it happens once, like the first picture of crossing over I showed you. Sometimes it happens twice, like this picture. Sometimes it's a medium-sized chunk, like in these 2 examples. Sometimes it's a little tiny chunk. Sometimes it's a big chunk. So it's all completely random. So yeah, you'll have those 64 trillion different combinations. But then if somehow you could somehow get that same exact egg and same exact sperm again, based on independent assortment, you still would have different chromosomes because they've done crossing over. So the chances of you having those same exact chromosomes and then them also having the same exact crossing over events for each 23 pairs of your chromosomes, it's essentially impossible. Then again, so is 64 trillion. That's also essentially impossible because humans don't usually have that many kids. When I say usually, I mean never. Actually, let me think about that too. I have 8 billion people on Earth right now. So you do the math. Or you could look that up. That'd be an interesting independent work question because I don't think I know the answer. How many humans do they estimate have ever lived, including the 8 billion and some change that we have right now? Because I bet even then it's not 64 trillion. Which again, those numbers mean if your mom and your dad procreated 64 trillion times, then each time it would be different offspring. Only by independent assortment. Then you throw crossing over in there, and the numbers get even more. All right, so are there any questions about the origins of genetic variation, which will be important when we talk about genetics and evolution? All right, so just like when we talked about mitosis, we talked about, hey, what happens if that goes wrong in mitosis? And the answer was basically cancer. Then I believe it was Parks that was asking about, well, what happens if they don't separate the right way? I think you asked that, but here it is again. Now we're finally going to talk about it. When meiosis goes wrong, that's what we're going to talk about here. What happens when we have errors in meiosis? Well, it can result in genetic abnormalities ranging from mild to severe to fatal. So some of the mild/severe ones you should be already familiar with since you've already done the lab this week, I'm sure, even though it's not due until later today. But you saw those different karyotypes, right? All these different, like some of them had extra chromosomes. Well, this is an example of that. Obviously, if there's a syndrome for it, those were not fatal, right? Because those are people, because again, if you read each one of them, there's different prognosis, and you learned about what they are. But if they're fatal, they don't even make that list because, there are no symptoms. The zygote just never developed. So here we go. How accidents during meiosis can alter chromosome numbers. Here's what you basically need to know. After everything I teach you, this is the big thing you need to know. Which is not after everything I teach you. Everything I'm about to teach you, the most important thing is you know what non-disjunction is. Non-disjunction is when a chromosome pair fails to separate at anaphase. Right, so they're there together at metaphase. And remember, anaphase is defined by the fact that they've been separated. So with non-disjunction, they just fail to separate. And I like the wording here. I don't think I've used this term before. Chromosome pair. Because if it's in meiosis 1, we're talking about the homologous chromosomes didn't separate. But if it's in meiosis 2, then the sister chromatids did separate. So it depends on which one it is. Anyway, that's why I like that generic term, chromosome pair. So we could be talking about homologous chromosomes. We could be talking about sister chromatids. Either way, if they fail to separate, it's called non-disjunction. As a matter of fact, if I were doing a flashcard, I would just put non-disjunction on one side, and then on the other side, I might just put chromosomes fail to separate. Yeah, of course, technically it's a chromosome pair because we're either talking about homologous chromosomes or sister chromatids. And yes, obviously it's happening at anaphase. But what you need to know for the exam is the non-disjunction is when they fail to separate. Obviously, if they fail to separate, then the end result, when you're looking at the gametes that are produced, are going to have an abnormal number of chromosomes, right? So if some of them fail to separate, imagine it, and I'm going to show you a picture, a couple slides, and that'll make it a lot more clear. But imagine chromosome pairs failing to separate, right? That means the cells that got the ones that failed to separate now have too many chromosomes. The cell that didn't get the chromosome that it was supposed to now doesn't have enough chromosomes, right? So it always results in at least one cell having too many chromosomes and at least one cell having not enough chromosomes. I put this in red because I might ask you this. It can occur, as I've already mentioned when we talked about homologous chromosomes versus sister chromatids. It can happen in meiosis 1 or meiosis 2. Either one is possible. And again, meiosis 1, we'd be dealing with homologous chromosomes failing to separate. In meiosis 2, you'd be dealing with sister chromatids failing to separate. Any questions about this slide?
Gametes are the sex chromosomes?
Sex cells.
Sex cells?
Thank you for asking. Should have reminded you of that, yeah. So gamete is it's a generic term for sperm cell or egg cell. Which is a lot easier. Past couple of slides, I kept saying your sperm or your egg, right? It would have been easier to just say gamete. So your gametes are your sperm cells and egg cells. Here's some stuff I'm going to put a question mark next to this. I'm not quite sure I'm going to ask you this. Big question mark. But let's talk about it anyway. The next word for attendance, I'm pointing at it. I'm not going to say it. There's the next word for attendance. So if you're at home watching the video, listening with your eyes closed and you're relaxed, open your eyes and look at what it's being pointed at or what it's pointing to. So anyway, if this does not happen, if non-disjunction doesn't happen, everything goes as it's supposed to, and you have the correct number of chromosomes, that's called euploid. Which is funny, that's another ploid. So far we've talked about diploid, which is a full set of chromosomes, haploid, which is half the set of chromosomes, and now euploid, which is the correct set of chromosomes. Of course, if that doesn't work, and we do have non-disjunction, and there are some cells, some gametes, that have too many or not enough chromosomes, we call that aneuploid. So a way to remember that too, an, prefix an, basically means like not, or maybe anti, right? So if euploid is the correct number of chromosomes, and aneuploid is like not the correct number of chromosomes. Then it gets even more, I don't want to say complicated, but more terms to remember. If one of them didn't get enough chromosomes, therefore it's missing one chromosome and only has the one chromosome, we call that monosomy, or monosomy, however you want to pronounce it. And then, of course, if it gained an extra chromosome, so it has 3 instead of 2, that's trisomy. Is that?
Ever more or less?
What's that?
Is it ever more than one?
Yeah.
They probably die.
It probably would, but not so much with plants. So to answer your question in the context of this course, what you're going to be tested on, then the answer to your question is no, it will always be this. But to answer your question in all actuality, yes, it can be different than this. Matter of fact, in plants, it's a lot more common, and we use this on purpose. In a sense, we kind of do this with, like, for example, watermelons, seedless watermelons. This is how they're created. We can force the watermelon plants to have 4 sets of chromosomes, so not trisomy, but 4. And then we breed those with other sets, regular watermelon, and then you have some weird in between. And because it's a weird in between, the completely healthy watermelon plants, except they're hybrids, so they can't reproduce. Just like a donkey and a horse come together to make a mule. A mule is completely healthy, it's fine, but it can't reproduce. So again, for the exam, as far as we're concerned in this 100 level non-biology major class, that's the story. But like you did say, there are exceptions, and you can look for those exceptions in for independent work if you want. what happens if it has two extra sets of chromosomes. As a matter of fact, there is one example in the lab, even though you don't need to know it for the exam. If you remember, one of the conditions had an X and then 3 Ys. And technically it's a trisomy, but really it's kind of different because now you have 4 extra sets of chromosomes. It's just a little bit more unique because they're sex chromosomes. So anyway, any questions about this slide? Next slide is going to show you a picture of non-disjunction of meiosis 1 versus non-disjunction of meiosis 2. So here we go. Non-disjunction of meiosis 1, you can see those two homologous chromosomes separated just fine. These fail to separate. So then the cells get split. The one to the left that have these extra set of chromosomes now has extra chromosomes. The one on the right that didn't get the set of chromosomes that it's supposed to now has not enough chromosomes, right? And then it goes through the second round of meiosis. So then they get split. And what we're left here was 2 cells that have too many chromosomes and 2 cells that don't have enough chromosomes. Now in meiosis 2, we're not dealing with homologous chromosomes failing to separate. We're dealing with sister chromatids failing to separate. So the interesting thing about this, if you want to call it interesting, slightly interesting thing. Here, because we had one good round of meiosis, right? So those things separated like they should. So at the very least, even though this one got messed up, at least we do have one normal cell. And then it goes through its round of meiosis. So now we have 2 normal cells. But here, this one, again, it failed to separate, it's non-disjunction. So this one has too many chromosomes, this one has not enough chromosomes. So maybe I'll ask you this question. You might need to know something like the difference between non-disjunction of meiosis 1 versus non-disjunction of meiosis 2. Again, if it's meiosis 1, then this is, right, first of all, you need to know the reasoning behind this anyway. So even though I might not specifically ask you this question about the difference between non-disjunction of meiosis 1 versus non-disjunction of meiosis 2, the things I'm about to say are things you need to know anyway, right? So in non-disjunction in meiosis 1, we're dealing with homologous chromosomes. So it's the homologous chromosomes that fail to separate, right? So again, regardless of if I ask you this specific question, you need to know in meiosis 1, we're dealing with homologous chromosomes. Versus meiosis 2, which is where we're dealing with sister chromatids. So think about the things you need to know, which is that meiosis 1 deals with homologous chromosomes, and meiosis 2 deals with sister chromatids. Then if I were to ask you this question, again, you should already kind of know that background information, so hopefully it's already there for you. And another thing to consider, and this would be a little bit harder, but consider if we're dealing with non-disjunction of meiosis 2, then we at least then have one normal cell that got split, which then leads to 2 normal cells. So if it happens in meiosis 2, we at least get 2 normal, I'll start saying gametes instead of cells. They're both cells, gametes are cells, but let's say gametes more to help illustrate that point. Here we have, again, 2 normal gametes. Here we have one gamete with not enough chromosomes and one gamete with too many chromosomes. And of course, here we have 2 gametes with not enough chromosomes and 2 gametes with too many chromosomes. I will put some X's through here. This is good to read and help you understand things, the n+1, n-1. But for the exam, if I ask you any questions about this, I will not be using n, 2n, n-1, n+1. I'm not going to use that. I'm going to use the words to describe it. Too many chromosomes, not enough chromosomes, the right number of chromosomes. What's the other one? Aneuploidy, right? Euploidy, the right number of chromosomes. Aneuploidy, not the right number of chromosomes. So I'll use the words, not the n+1 or anything like that. Any questions about that particular slide? Okay. The next slide I'm going to show you, which again is not in your textbook, it's from the old textbook, just like a lot of these pictures I've been showing you. It's going to show an abnormal gamete. So an abnormal sperm or egg fertilizing a normal gamete. So normal sperm or egg. So now we're not just looking at the results of meiosis, which is what produces your gamete, your sperm or egg. Now we're going to take it to the next level, the next step, And look what happens when you have one of these messed up sperm or egg coming together with a normal sperm or egg. In this particular example, the result is going to be a zygote that has 2 N plus 1 chromosomes. And again, for the exam, I'm not going to describe it like that. For the exam, it would say something like, the result is a zygote with an extra chromosome. Or an aneuploidy chromosome, right? Because aneuploid means not the right number. So we have this zygote that has too many chromosomes, and that's how we all started life, was one zygote, right? At one point in our life, we were one cell. When that sperm and that egg came together, we were one cell. And then we copied it, and copied it, and copied it, and copied it, and copied it, right? That's what mitosis is. And it's a perfect copy. So if the resulting zygote, if the zygote has a flaw in it, then every single copy that's going to be made from that is going to have the same flaw. Just like if I were like, have a piece of paper, and was like, hey Harrison, can you go please make a copy of this? And she takes it, she goes makes a copy of it, but I accidentally, I don't know, drip some coffee on it. So it's got a little smudge on it. Now she's going to make a copy, and then she's going to give it to someone else, and they're going to make a copy, and they'll give it to someone else, and they'll make a copy, so on and so forth. Every copy of the original is going to have the smudge because it's a perfect copy. So if the organism survives, right, the organism that has, in this one example, this one extra chromosome, if it survives, it will have an abnormal karyotype, which you should be familiar with from the lab that you did Wednesday. And it'll have a syndrome of disorders caused by an abnormal number of genes. Which is a good time for me to tell you this, because I don't think I emphasize this enough. All that karyotype stuff, this syndrome and that syndrome, it was great exercise. It was good for you to know, but there'll be no test questions. There'll be no questions where I say, what's it called when there's an extra set of chromosome number 13? What's it called when there's 2 Y chromosomes instead of 1? Right? I'm not going to ask you the names of the genes. So it's interesting stuff. Maybe one day relevant to your real life. But not important for the exam. Anyway, let's look at it. Here we have a normal sperm cell. Here we have an abnormal egg cell. You can see this one's got, I don't know, let's call that chromosome number 1, chromosome number 2. Whatever species this is, it only has 2 sets of chromosomes, right? So here we got chromosome number 1, chromosome number 2. Here in the egg, we have 2 chromosome number 1s and only 1 chromosome number, and then 1 chromosome number 2. You bring them together. Chromosome number 2 now has the normal set. Chromosome number 1 has that extra long chromosome in it. Or, right, here this one's N for normal, N plus 1. It's not normal, it has 1 extra chromosome. And the result is a 2N plus 1 zygote. And once again, I'm going to put some X's through here to remind you, even though it's on the textbooks, I don't like using those. N, 2N, N plus 1. I won't be using that. I'll be using the words to describe the condition. A sperm with a normal set of chromosomes fertilizes an egg with an extra set of chromosomes. What is the result? A zygote with an extra chromosome. Right? I use the words instead of the whole N plus 1, 2N, all that stuff. Any questions about that slide? All right. So your old textbook, and I think the new textbook too, just gives us one example, right? Because it is the most common. So if I ask any questions, I know I just got finished telling you all that stuff you learned in the lab at the end, that table, that I wasn't going to test you on that, and I'm probably not, but if I did ask you anything, it would be about this one. Trisomy 21 is when there's an extra number 21 chromosome, as the name indicates. So instead of having a pair, chromosome number 21, there's 3 of them. So that means then instead of having the normal 23 pairs of chromosomes, well, I guess you can still kind of say that, but instead of having a total of 46 chromosomes, like a human should have, that would be 47 chromosomes. But really quickly, just to point this out, as you should be familiar with from the lab, just because there's an extra chromosome, right? If you have 47 versus 46, that doesn't necessarily mean it's trisomy 21, right? It could be an extra chromosome somewhere else, but in this particular case, it's the 21st chromosome that has an extra. So a person with trisomy 21 is said to have something called Down syndrome. It affects about 1 from every 850 children born, I think, in the United States. That I'm not sure of. You could look that up. I'm not going to ask you, but there's a number you could, easy independent work where you don't write a paper. You just write me an email, not in a Word document. You just literally send an email. Like, I looked it up, and according to this source, worldwide there are this many children born with Down syndrome. Or in the United States, there are this many children born with Down syndrome. Or in third world countries, there are this many, whatever it is you want to look up. There's so many different possibilities. And again, you can just send me an email, tell me the question you were looking up, give me the answer, give me your source, automatic 1 point. You don't have to worry about plagiarism or copying. You can just put quotation marks and give me exactly what that source says. Or you can write a paper about it. And that's when you would want to use Google Docs. And that's when you get graded on how well you wrote it and how long it is. Anyway, most chromosome abnormalities, this is the most common chromosome abnormality, which is why it's included in most textbooks, which is why I might ask you about it. Still probably not, though. It is also the most common serious birth defect in the United States. That was also in 2016. I would assume it's still the same. Again, not just this, but anything I tell you, please look it up. But especially when I give you statistics, because obviously statistics change. So you can look that up for for independent work too. Is that still true? Is it still the most common birth defect in the U.S.? Then again, what about worldwide? What about, choose your favorite region of the world or your favorite country? Look that up if you want. Another thing that's pretty commonly known is the risk of this happening increases with the age of the mother. There's a particular, never mind, that's the next bullet point. 35 years is about what we're looking at, right? 35 years and older, that's when it's even higher risk. So those mothers are candidates for prenatal screenings. I'm definitely not going to ask you the age for the exam, but that's just something to consider. And another thing to consider is for independent work, why? What happens as women are getting older that this is a higher risk? Conversely, or maybe not conversely, but what is it about men? Why is it that, for example, who is it that just had a kid? I think Mick Jagger, some older gentleman. When I say older than me, older than Kesterson, an older man, just had children. So why is it that their risks go up? Why is it always the age of the mother? Something you could look up for independent. So I guess on that note, the next word for attendance would be the Rolling Stones. We'll look at the next slide, which is again furthering this conversation. People who have Down syndrome have characteristical face features. I'm sure you've seen somebody with Down syndrome. You can see somebody, generally speaking, it's like, yes, they look like they have Down syndrome. They generally have a shorter lifespan, usually but not always. And you can look that up for independent work if you want. I actually don't need to know the answer to that question. What is the average lifespan for somebody with Down syndrome, and how much does it vary? Or let me rephrase that, because that's kind of like two different questions. What is the average lifespan of someone with Down syndrome, and or how much does it vary? It's like if everybody who's ever had Down syndrome on Earth died at the age of 45, and then 10 people who've ever lived died at 35, or excuse me, 55, then you would say, well, those 55 was really an outlier. So there's some variation, but not much, in that hypothetical example. Anyway, there's also varying degrees of developmental delays, so they're not all the same, which is also fascinating to me, because if it's just caused by an extra chromosome, the same extra chromosome, right? So chromosome number 21, whatever genes they have on their chromosome is the same genes that we have on our chromosomes. Different versions, but we all, again, they're homologous chromosomes, right? So a homologous chromosomes carries the same genes in the same spot. So they have the same genes that we have. They all have the same extra chromosome, which has the same genes on it. So why are there varying degrees of developmental delays? You look that up for independent work. It looks like this is a little bit out of order. This bullet point should be kind of up here, but some may live to be middle age or beyond. And many are socially adept. No, I guess never mind. That is a good place for that bullet point because it kind of brings together the 2 bullet points above it. Any questions about that before I show you some karyotypes? All right, this is a normal karyotype. You can see each chromosome comes in a pair, right? Including chromosome number 21. And then here is an example of trisomy 21. So again, they all look the same, except this one there's an extra chromosome. And one thing I say every semester, and I always say I'm going to look it up. I don't think I have. So someone probably already knows the answer to this, but my hypothesis, my question is, why is this the most common genetic abnormality? Why isn't it an extra chromosome number 13 or 2? And my hypothesis is, look how small chromosome number 21 is. Obviously, the smaller it is, the fewer genes it has, right? The less genetic material it has. Therefore, if you mess up something really small, it's relatively a small mistake. Meanwhile, if you're having an extra chromosome number 1, which is the largest, that's a much bigger mistake. That's a lot of extra genes, right? Because that's a big chromosome. So that's my hypothesis. I'm not sure if it's true or not. You can look it up. Is it like the smaller the chromosome, the less deadly it is? Because I would assume, speaking of which also, I would assume the non-disjunction happens equally. The probability of having too many 8s would be the same as having too many 16s, for example, is my assumption. I don't know this. But my assumption, my hypothesis is the smaller the chromosome, the less deadly it is. Therefore, it's more common because they actually survive. Again, I'm just hypothesizing here, but I assume since chromosome number 1 is so big, I would assume having too many of them would be deadly, therefore they're never born, therefore it's not common. And that's the last thing we'll talk about. Perfect timing. When we come back on Friday, we'll finish up this chapter and start the next one. And Friday will be the last word for attendance. So I will see you guys in office hours or on Monday. And remember, I'll be gone this weekend. So I apologize in advance for being hard to reach. Enjoy homecoming if you get to stay and you are participating.